Astrophotographer Satoru Marada has just captured what many scientists now consider the most crucial observational breakthrough in the entire 3I Atlas investigation so far. Working from New Mexico with a modest 0.2-meter telescope, he compiled 24 separate 60-second exposures, stacking them with advanced Sigma clipping methods to extract an image with astonishing resolution and purity. And what this image revealed has fundamentally reshaped the scientific narrative around this interstellar object. The tail stretches an almost unbelievable 2.6 million kilometers into space. That isn't just impressive, it's 7 times the Earth-Moon distance. To truly visualize this scale, imagine driving along a straight cosmic highway at normal road speeds. It would take over 3 continuous years to travel the full length of this tail. But the sheer distance isn't what has astrophysicists buzzing. It's the architecture of this tail that's generating shockwaves. Instead of diffusing into a broad expanding plume, as every known cometary model predicts, 3I Atlas's tail maintains a razor-thin, precisely defined column for its entire multi-million kilometer extension. In normal comet physics, heavier dust grains spread outward in ballistic arcs, while finer particles fan out under solar radiation pressure, creating wide luminous veils. But here, none of that is happening. Instead, particles seem to be traveling along what can only be described as a cosmic pipeline, maintaining tight cohesion as though guided by an unseen organizing mechanism. This could indicate an extraordinarily uniform particle distribution, something almost never seen, or a stabilizing force that preserves alignment far beyond the limits of conventional physics. Marada's image also reveals multiple simultaneous jets erupting in directions that defy standard comet behavior. Some jets shoot directly sunward, while others fire away from the sun, forming a near-symmetrical pattern that hints at an intricate internal network of channels, fractures, and gas flow pathways. The symmetry suggests a structured, consistent internal architecture, not the chaotic random venting normally seen. Even more intriguing is the clearly defined anti-tail, a sunward-pointing structure caused when Earth crosses the object's orbital plane. Anti-tails do occur in some comets, but they're usually fleeting, lasting only while the viewing geometry is perfect. Yet the 3I Atlas anti-tail remains stable, sharp, and extended well beyond typical durations. This persistence suggests either unusually large particle emissions or highly selective directional venting. Confronted with this unprecedented combination of anomalies, researchers have consolidated their interpretations into 3 main theoretical frameworks. Theory 1. The extreme natural hypothesis. One possibility is that 3I Atlas represents an exotic but still natural cometary specimen, existing at the extreme boundary of known physical behavior. Under this interpretation, the nucleus contains unusually high concentrations of low-temperature volatile ices, such as carbon monoxide and molecular nitrogen, which can sublimate even in the frigid outer regions far from the Sun. This could sustain continuous outgassing at distances where typical water-ice comets lie dormant. Its stable rotation might indicate an unusually rigid and dense nucleus capable of resisting the twisting torque normally generated by uneven gas jets. The reflective surface patches could be exposed reservoirs of these volatile ices. The rhythmic cyanogen emissions might result from deep internal vents that activate only when specific regions rotate into sunlight, creating a natural timing sequence. This model keeps 3I Atlas within the domain of physics we already understand, just at the most extreme edge. Theory 2. Observational/geometric illusions. The second explanation argues that many of the apparent anomalies may be due to our angle of observation, the object's orbital configuration, and the constraints of our measurement tools. The unusual viewing geometry between Earth, the Sun, and the orbital plane could be making structures appear more coherent and stable than they actually are. The observed stability of the thrust signatures might simply be a limitation of our detection sensitivity. The periodic behaviors might be artifacts caused by irregular observation schedules rather than true synchronized cycles. In this framework, 3I Atlas is ordinary, but our perspective is extraordinary. Theory 3. Unknown physical processes. This is the most speculative but also the most scientifically honest interpretation. Some researchers believe the behavioral patterns, consistent, stable, finely structured, may indicate physical mechanisms unknown to cometary science, possibly involving material properties unlike anything found in solar system objects, extreme interstellar radiation conditioning, formation in environments radically different from our Sun's protoplanetary disk. This theory does not require anything artificial or engineered. It simply acknowledges that interstellar travelers may obey physics we have not yet integrated into our models. 3I Atlas may be showing us a category of matter shaped under conditions no Earth-based laboratory has ever replicated. Why December 19 matters? December 19 marks the closest approach of 3I Atlas to Earth, a moment every observatory on the planet is preparing for. This global campaign involves massive ground-based telescopes, space-based observatories, and specialized instruments all gathering synchronized data. Scientists are focusing on 1. Particle velocity measurements. If cyanogen jets move at hundreds of meslas, the natural sublimation theory gains strength. If they reach kilometer per second speeds, we enter uncharted physics. 2. High-precision spectroscopy. This will reveal chemical compositions, isotopic ratios, and potentially exotic materials never seen in solar system objects. 3. Bright patch evolution. Tracking whether reflective regions grow, shrink, or hold steady may expose internal structural patterns. 4. Long-term thrust monitoring. If thrust stability continues beyond the 182-day record, conventional physics will struggle to explain it. Simultaneous imaging from multiple locations will help reconstruct the 3D architecture of the tail and jets. Why 3I Atlas is a landmark scientific event. 3I Atlas is only the third confirmed interstellar visitor ever studied in detail. The first, Oumuamua, challenged physics with its unexplained acceleration and bizarre geometry. The second, 2I Borisov, resembled a comet but had unusual chemical signatures. Now 3I Atlas brings an entirely new suite of anomalies: tail behavior, jet symmetry, rotation stability, thrust consistency, and extraordinary structural coherence. Each of these objects carries the chemical fingerprints and structural clues of the environment where it formed, far beyond our sun's influence. They are natural interstellar messengers, drifting for millions of years before arriving in our sky. 3I Atlas is already reshaping cometary science, interstellar chemistry, solar system dynamics, our understanding of matter formed in alien environments. Whether the final explanation is extreme natural physics, observational effects, or mechanisms we've never theorized, 3I Atlas is pushing the boundaries of everything we thought we understood. The real-time mystery. What makes this moment profoundly exciting is that it's unfolding live. We're not analyzing ancient supernova light or theoretical models. We're studying a real object, here in our solar system, behaving in ways we cannot yet explain. So the question becomes, are we witnessing the most extreme natural cometary behavior ever recorded? Or is 3I Atlas demonstrating that objects born in other stellar systems operate under rules we've never imagined? We won't have to guess for long. The data is coming, and when it arrives, it may rewrite entire chapters of astronomy.